Hi, my name is Stephen Blumenthal, and I'm going to tell you about my final project for ENME489y at the University of Maryland. The goal of this project is to use a Raspberry Pi and OpenCV platforms to design, integrate, and test a field-deployable LiDAR. Each student has to identify an object on campus at the University of Maryland, use their sensor to take measurements, and finally, use the data to create a digital 3D point cloud and mesh of the physical object. The overall purpose of this is to give students the opportunity to get hands-on experience with real-world remote sensing. The object I chose was the free library stand next to the Center for Young Children. As you can see on the right, the object is located on North Campus behind Oakland Hall. I chose this object because I thought the simple shapes and sharp edges would help me create an accurate point cloud. Moreover, the object has both narrow and wide faces at various depths, which I thought would be a good way to test my LiDAR's capabilities. Before I get into more detail, let's first talk about the fundamentals. So first, what is remote sensing? Remote sensing is the science and technology of obtaining information about a target without having a sensor in direct or physical contact with the target. This includes LiDAR, radar, and sonar. However, this project focuses solely on LiDAR, or light detection and ranging. The most common way of collecting information for all types of remote sensing is by using the interaction between radiation and the target. If the radiation used is naturally occurring, such as sunlight, this is referred to as passive remote sensing. Conversely, active remote sensing is when the radiation is self-generated, such as the light laser used in this project. How does this all work? First, radiation is generated by the radiation source, in our case the laser light. The radiation travels through the environment until it contacts the target's surface. The radiation is then backscattered by the target and travels back to the detector where the information is analyzed and processed. For my LiDAR, the sensor is an 8 megapixel Raspberry Pi camera, and the transmitter is a laser. Initial calibration used a green laser pointer. However, most tests used a red line laser. The line laser allows me to capture more information in a single measurement. My initial setup was pretty basic. I used duct tape and boxes to position the camera and laser parallel at a distance of 12 inches apart. My target was a table with a white piece of paper taped to it. I then took data as I moved the target away from the laser at increments between 0 and 10 feet away. As you can see, the laser dot moves closer to the center of the camera frame as the target moves farther away. This information is important because we can use it combined with the triangulation LiDAR range measurement technique to determine how far away a point is from the LiDAR. Triangulation LiDAR range measurement technique sounds complicated, but it is just simple geometric calculations. As you can see in the diagram, the LiDAR configuration creates a right triangle. Basic geometry tells us that the distance to the target is equal to the distance between the laser and the camera, divided by the tangent of angle theta, where theta is a function of the number of pixels from the center of the focal plane, the radians per pixel pitch, and an offset term to compensate for error. For the data that I collected for my initial calibration, I used RO equals minus 0.05 and RPC equals 0.001. Here you can see my data in red compared to the theoretical values in blue. My LiDAR was very accurate above 5 feet, and then the accuracy begins to decrease. However, due to the rudimentary nature of my initial calibration, I considered this a successful proof of concept test. Before I move on, I want to quickly touch on computer vision. Computer vision is the science and technology of using a computer to gain high-level understanding from an image. For this project, we used an open-source computer vision library called OpenCV. OpenCV allows us to transform an image into meaningful data somewhat autonomously. We will get into how I specifically did this when we talk about object data processing. Alright, so here we have our LiDAR sensor configuration. As you can see, the whole thing is placed on a holder that holds it rigidly to this tripod that we see. We have the Arduino here, which is powering this line laser. As you can see, it is a line laser. It is creating a line laser across the room. So we have the laser, which is our transmitter, and our receiver is the camera, which is connected to the Raspberry Pi, which is mounted here. And it is mounted like this. You can see it's rigidly mounted 12 inches apart. Calibration of the line laser was conducted the same way as before, taking measurements at increments of half a foot between 2 and 10 feet. As you can see, an RO value of minus 0.00000011 and an RPC value of 0.000116 gives us a value very close to theoretical. Now that the LiDAR is calibrated, we are ready to test it on a physical object in a controlled environment. Alright, so this is my setup for testing my LiDAR system. It's up here. And so the laundry bag is positioned on this table. The laundry bag is approximately 5 feet from the LiDAR sensor, and the LiDAR is 6 feet from the wall. The laundry basket itself is about 2¼ feet high and about 13 inches across, and it is approximately 2 feet off the ground. And so we're going to be scanning this at increments of 2 degrees from negative 20 degrees to positive 20 degrees. Since the method of converting the images into a 3D point cloud is the same for both this test and for my object scans, I will skip ahead to my results and explain the processing later. So you can see here, and finally here is probably the better 3D point cloud. So as you can see, you can clearly see the wall in the back where it's all flat. You can see the outlines of where my laundry bag is. You can clearly see that it is rectangular in nature, a little round, which is true. It's a soft bag. You can see the depth of the bag compared to the wall, and you can see how it is off the ground. I think this came out pretty well. Alright, so here I am at my target. So here you can see my LiDAR sensor set up. I am right there, and there is my target. It is one of those free libraries, give one, take one, on campus, about near the North Campus dorms. And so as you can see, there's some critical features of this target that are interesting to scan. You have the thin post at the bottom. Maybe even we can get some of the features underneath, but I'm not quite sure. Then it expands, and then we have the slope of the roof. Hopefully we can catch all those and their sharp shapes, so hopefully that will help. And as you can see, the LiDAR is set up here, ready to scan. Unfortunately, I'm going to use my phone for the angle measurements, so I will switch to my computer. Of course, it's never that easy. I had a few problems. The first problem was the glass door and the books behind it were giving me funky results. To fix this, I simply taped paper over the glass. The next problem I had was with the roof. A spotlight was shining directly onto the roof, flooding my camera with light. This made it extremely difficult for the camera to capture the laser line. I tried taping white paper to the roof, however, this had no effect. I simply accepted that I was not going to get any data from the roof. The last problem I had was that the right side of the library was blocked by another library. This prevented me from scanning this side of the object. Since the right and left sides are identical, I used a rotated version of my left side scan to complete my point cloud / mesh. So my computer ran out of battery, so this is me trying to collect the final 2 shots that I have left. Now that I have all my data, my first step is to use Python and OpenCV to manually select the bounds of my HSV mask. By using the OpenCV library, I was able to assign all of the pixels a red, green, and blue color value between 0 and 25. Since the laser line is the only information I want, I use these values to filter out any colors that are not the laser line. These are the values that you see here for color lower and color upper. I then put in the offset setup values I use for calibration, and then we have the distance here. And you see that using the Python code and the OpenCV library, we are able to cut out some of the image that we don't need, blur the image to smooth the transitions between colors, apply the mask, and then once the mask is applied, we can use Python to determine how far away the leftover pixels are from the center of the frame and use the equation that we got earlier. The Python script exports a text file with the 3D X, Y, and Z coordinates of every data point. I then import this file into MATLAB using this code here. Using MATLAB, I can combine the individual text files into one point cloud. I can rotate a dataset by 90-degree increments by multiplying the X and Y arrays of the dataset by -1. I did this here. I can also use addition and subtraction to translate the datasets, which I have also done here, and to the other datasets. Since I know the orientation and distance of the object for each dataset, I was able to combine the datasets into one point cloud without too much trial and error. So this is what the raw point cloud looks like. As you can see, there is a lot of extraneous points and a lot of noise. This needs to be filtered. Using the shown MATLAB code here and other occurrences, I was able to filter out the points above or below the known values of the object. I then combined the data into one text file and plotted it using this file to combine and then plotting the point cloud here. So this is the filtered point cloud. As you can see, it came out pretty well. There's a lot less noise than there was before. You can see that it is skinny on the bottom and fat on the top. It has the triangular shape on the sides and the square surfaces. Unfortunately, like I said before, I was not able to get any data from the roof, but that's okay. You can even see the small depression from where the glass panel is on the front door. Overall, though, I think it looks like the object. And if you're not convinced, here's an overlaid image of the point cloud onto a picture of the actual object. As you can see, it's pretty close. To Mesh Lab. So I create a new mesh, and what I'll do is I go to File, Open, and I find the file that I created, the combined text file with the data points. I'll click space, OK, and here you can see are all of the data points that I've created. Now, in order to create a mesh, there's a couple steps. We first go to Render, Show Normal, and then we want to create the normal, which basically says where the planes are. So we go to Filter, Normals, Curvatures, and Orientation, Compute Normals for Point Set. Now, I can't tell you how I found these values, but I found out that these values work if I use 1750 for neighbor numbers, turn on Flip Normal with respect to orientation, and click Trackball Center, and hit Apply. You see I've created all the normals. They're all pointing away, so that you can just kind of see where the faces are going to form. Next, I want to go to Filters, Remeshing, Simplification, and Reconstruction, Screen Poisson Surface Reconstruction. Again, through trial and error, I found out what works for me, so I hit 3, and I hit this Merge All Visible Layers button, hit Apply, and then I hit the mesh. You can see I've created my mesh here, and it's actually a lot better than I expected. Overall, I thought this project was a success. That's all I have. I hope you enjoyed. Thanks for watching. Bye.